Hello and welcome back to my series on mathematical modeling of the coronavirus outbreak. This video, we're going to look at the question of ending the lockdown. How do we manage to get out of the lockdown, and is it time yet, and what are the dangers? So to begin with, let's look at the mathematical modeling process. A lot of people have been talking on television about it, and a lot of people seem to expect the modeling process to predict the future, which is, of course, ideally what we would like to be able to do. But in fact, the modeling process is a way of learning about the disease and the transmission of the disease and characteristics of it, as much as it is about trying to predict the future. In fact, predicting the future is not the most important. So what do we do in the modeling process? What is involved in it? First of all, we have to identify what we think the important measures and assumptions are. Those have to be very precisely defined. Then we have to postulate as well the relationships among those measures and how to apply those assumptions as well. The important philosophy or philosophical point of view in doing mathematical modeling of anything, in particular epidemics, is that if something happens in this ideal world of mathematics, if we discover something or if we try something and have a certain effect, will we actually observe that same effect in the actual data in the real world? The presumption is usually yes, and if not, it gives us reason to try to research that even further to see, to have a better correlation between our mathematical models and reality. So then to do that, we compare the results of the mathematical model with the observed data to see if the match is good or not. If it's not good, we have to change the model. We have to explain the different relationships or in some way decide what it is that we're doing that's not exactly right. If the match is good, then we can actually start with that model and use it to see how we might be able to treat the model and see if that that same treatment would be reflected when we do that in the real world. Another very important point is that a lot of times we can explore things in the mathematical world that are not possible or that are very expensive or would take a tremendous amount of time to do in the real world. So that's a bit about the starting. We're going to go through this modeling process and look at some of the models that we've talked about so far. So I want to go to the last model that we talked about. This you'll recognize as the program, and I have changed this, but I want to go back and see some of the essential points that we did in this particular model. This is the SIIR model, so it's the model where people were initially susceptible, then become infected but are asymptomatic, still able to transmit the disease. Then they go from the asymptomatic group into the infective group where they are actually symptomatic and infective, I should say. So they're symptomatic, but I'm calling them in this model the infectives. And then they recover from the disease at a rate of rho and go into the removed portion of the population. So these people are immune to the disease. And we're presuming then, since we did say that we want to identify all the important relationships, we are presuming that this immunity is permanent. Now this was, if we think back on this model from the previous video, the S, A, I, and R were actually fractions of the population. And by considering this to be fractions of the population, we had the derivative of n, the number of people in the population. So we went through this analysis, and at the end of the analysis, we actually presumed, without saying it expressly, I should have maybe, but that the population remains constant throughout our time that we're looking at. So we were looking at the population of France, and so the population of France is 67 some odd million, so we put that in at the end. Just in the case of the coronavirus, we do in fact have a change in the population. People are dying, not tremendous percentages of the entire population, but still fractions of the populations that make it more interesting perhaps to allow that number of individuals in the population to vary. So in this video today, I'm going to add the the size of the population as one of the variables of the model. So we've done that now. I'm going to go to this particular model, and now we'll notice here that the big change is that I still have my asymptomatics, and they're still interacting and infecting people. But as we said before, the lambda is the number of contacts per infectious person that are adequate to transmit the disease if the person contacted is susceptible. So since now our letters here, SAIRN, are numbers of individuals instead of fractions of the populations that we had before, I have lambda people contacted multiplied times the A number of symptomatics, but now I actually have to divide by N to get the fraction of people who are susceptible. So this, and we see now for the same effect for lambda 2 is the contact rate for infectives who are symptomatic. So we have the asymptomatics and the symptomatics, each contacting people per unit time, but the number of people that they are, the probability of that person being susceptible is the S divided by the total number of population, because that's the fraction of the population that is susceptible. Now, this presumption is also quite important, this presumption for the infectives and for the symptomatic infectives, and also for the asymptomatic infectives. Why is that important? Because we're considering that the probability of the person contacted being susceptible is the same as the fraction of the susceptible population. What that assumption is, and this is why we have to look at this very closely, that's called homogeneous mixing, which means that this infective person or asymptomatic infective person as well are equally likely to contact any other individual in the population. And this is the assumption that will, for a lot of epidemiological models, including the ones we've done until right now, demonstrate a higher level of outbreak, a higher peak than you might expect, because we're dealing with the group of individuals that are equally likely to come in contact with each other. And if I consider that to be the entire nation, then I'm going to incorrectly, in a way, represent the transmission as being much larger, much more than it is. So you've seen, I'm sure, on the television, a lot of people saying that the epidemiological models do have high predictions, and that is true because we're presuming that we're dealing with a population that is homogeneously mixing. So how do you deal with that? How do you improve your model? How do you make that more realistic? Well, you would have to restrict your attention to a group or a geographical region that is homogeneously mixing, and then look and see how those regions interact with one another. So here in Eastern France, we were the earliest in the breakout of the coronavirus, and you can see that outbreak in the homogeneous mixing model should be limited just to Eastern France. And then we see that Eastern France then did spread out and contact the Paris region and some of the other areas, and spread that through essentially inoculating another group. So I'm going to run this particular example here. Notice that I did reduce my total number of people to just under 1 million. This is about 1 million people. And notice also the difference between this model and the one we had in the previous video is that here I have included my equation for n, whereas we eliminated it in the previous video. So if I run this, I'm going to copy that and plug it into R as usual and see what happens. So now you see my blue curve is my estimate and my red curve is the observed data. Now a difference between this particular model and the one we did in the last video is here I have taken the red curve as my data from Italy instead of from France. You'll notice that as we did in the previous video, the one on do we see the light at the end of the tunnel, I have this curve, observed curve is accelerating. I have a point of inflection about here, and then it looks like it's starting to decelerate. It's increasing the entire time, but it looks like it's decelerating. And notice then that my theoretical curve looks a little bit like that, but I have to try to adjust that. Now, looking back, there are mathematical ways of adjusting that curve, our parameters in the model to the observed data, but what we have here that we can manipulate with, these are our parameters here, our contact rates, our birth and death rates. Gamma is the loss of asymptomatic, the transfer to symptomatic case. Beta were the births, delta were natural deaths, delta D were deaths due to the disease, and then rho was our loss, our recovery rate, so that 1 over rho is the length of time that we would be infectious as a symptomatic infectious person. So if I take 1 divided by, I'm doing this on my telephone, 0.18, then that corresponds to a 6-day infectious period as a symptomatic person. So as I said before, we don't really know exactly what these lambdas, the contact rates are. This is one of the reasons that people want to do testing and want to see if they can get some idea of what these natural parameters are and how they for this particular disease. So looking at the curves here, remember that if I start playing with my parameters to try to make this curve fit better, then if I decrease my lambda, I'm going to move this curve, the peak, to the right and down. If I decrease my death rate, for example, I'm going to have more infected, so I'll move this curve up. But you'll notice here what we really want to do is we want to take the bottom part of the blue curve and move it up, and the top part of the blue curve and move it down. So we have to play if we're trying to fit this model by hand, which is not the most sophisticated way to do. I'm going to let's say reduce the lambda 2 from 3 down to 5. Now it's not a good idea to move several things at a time, because then you don't know where the effect came from. But you have to play with these models and run them many times to see what the effect is. Notice that this did move slightly to the right, but in the bottom here I had my the curve drop down more from what it was in the last parameter estimation. So notice what I did here is I changed the lambda 2 down to 0.25. Let's suppose this is a 15% death rate here, and that could be a little high. That's pushing that blue curve down. So let me lower that, let's say even to just to 10. I'm going to leave the 0.25 there as I had before. So let me run this way. Notice again, my bottom part of the curve that I wanted to move up did move up, but in fact the top part moved up as well. So I have to try to, I would like to grab that curve on the two ends, the blue one, and just pull it to try to get it to go closer to the red curve. But let's go back and look at the presumptions that we have in here in the model. What we've done here is we've gone through 50 days of observed data, and I've presumed that we've got one set of lambdas that stay fixed for the entire time. Now what we did in a previous video is that we changed this, which we can do in this one and we will, So we changed it and had one set of lambdas for an initial period of time, and then we changed the lambdas after, say, a public health campaign where we went into lockdown or something like that. So is it really realistic to imagine that we would just change that lambda one time? Notice here, though, the lambda 1 is the lambda for asymptomatic cases, and the lambda 2 is the lambda for the symptomatic cases. So I'm presuming here that the asymptomatic cases will not necessarily realize that they are infected, and so they will not be affected by a public health campaign as much as the lambda 2s, who are the obviously infected and symptomatic people. So how can we change this to try to incorporate some kind of a natural decrease in lambda 2 as a function of the publicity or the public health campaigns going on? So I've done a new model where here I've set my lambdas a little lower. The reason is that I've changed some of the other parameters as well. I've set the death rate down to 8% instead of 15%. But let's look and see what the major, there were two things I wanted to do. I wanted to be able to, this is the Italian data, so I wanted to be able to use a larger n here. Notice I still have the n as a function, so I can actually change the number of people in my population. But I wanted to get up into closer to 25 million, so that's part of the many times that I've run this to try to make it more realistic. But here, let's notice that what I've done to incorporate a public health campaign is that I've taken the lambda 2, and whenever my number of infective people, the number of symptomatic people, gets big, then people will reduce their contacts by little k over the population size. So when k is small, this is 1, so I'm just taking the same model that I originally had. But as I gets larger, and I'm going to get a larger fraction here, and so I'm going to start multiplying by my contact rate, but not by a whole lot, because if you notice, k is 360 divided by 25 million. But you'll notice when you start playing with these kinds of models is that they're very sensitive to parameter changes, or in fact, these significant changes in the parameters take place over very small intervals. So now with that, I don't want my rate to go down below 0, so that's why I've taken the maximum of 0 and this modification. So this factor, the max of 0 and 1 minus I k over n, is a way for me to slow down lambda 2 as n gets bigger. I multiply by something that reduces as the bigger n gets, the smaller the lambda gets. To check and see what kind of realism I might have here, this is 5 days and is an asymptomatic. I've not changed the natural birth and death rates. I've left them the same. 8%, although a lot of people are observing, a lot of countries are observing more than an 8% long-term death rate. 20 days of an infectious period is the more common presumption. And so let me run this again like we usually do and see what kind of a curve that we get. So this curve here goes away, and let me paste my program into R and run it. Notice that this does, with these parameters, give me a pretty good fit. There's a little bit of a difference there. We can fiddle with this more to make that better, but this is actually, for me, a pretty good curve, and it's for the entire Italian curve. And so we see that it's increasing and accelerating until we get to the inflection point here, and then it continues increasing, but it's decelerating going towards the point. And this is for the entire observed Italian data. So this is a good fit. And we've made some of our numbers a bit more realistic. So how might we go beyond the 50 days? What kind of a prediction does this make? Notice I've left my parameters to be exactly the same. Instead of going out to 50 days, I'm going to take my theoretical model and run it out to 100 days and see it has a really good fit for the first 50 days. I'm going to go out to 100 days and see how that works. I've added some more programming in here to try to calculate those points of inflection and how high the max gets. So notice that currently we have something like 93,000 Italian active cases. So I'm going to take this new program and plug it in for going beyond 50 days. And notice now, here's the first 50 days. This is the beginning part of the S-shaped curve that gets us up to day 50. And that part of our model and function fit very well with the observed data. I noticed that in fact we go through the peak and the curve starts declining. So remember here it was y2 was my variable for the number of cases. So if I just ask what the max is of y2, that's going to give me the maximum number of cases. And in fact, that's 93,749 is the maximum of that. So we were at something like 90,000, 91,000 or something for the Italian data. So this looks like Italy is starting to go down. It goes down slower than the usual kind of disease model that you've seen that have a bell-shaped curve where it goes down just as fast as it goes up. But this, we hope, has maybe a more realistic way of calculating the contact rates as a function of the lockdown. So now what would happen is one last model that I want to look at. I want to look at a model to see what happens if I end my lockdown. So here in this model, you'll notice I've taken the same parameters that I had before. I've got my same population size that I've had before, and this is the same model that I've been dealing with before. But now here at day 120, I'm going to stop my lockdown, and in this second part, I'm going to go back to my original 0.2 lambdas. My second lambda is going back up. And notice here in the ds and dA equations that this 1 minus term went away, meaning I'm not going to change lambda 2. I'm just going to go back to the original size, and I'm going to go from 120 out to 140 and see what happens there. So let's keep that from being printed out. I'm going to copy all of that and run it in R and see what I can predict if I just stop my lockdown and let everybody go back to work and to play. So notice then what happens here up to day 140 is that, remember the initial S curve up to day 50, that's still there. But it's because of the scale of everything, it's squished down so that but I still have the agreement. Then there was a slow decline that we went through here, the slow decline until day 120. At day 120, when I pulled out my lockdown and let everybody go back, boom, the epidemic exploded again and went up to several million cases. So in fact, this model will predict that you should be careful and not go back to your old ways, or the disease will go back to the original prediction. So I'm going to do one last run and then we'll stop for today. I'm going to go out here where I did my first 100 days, and I'm going to take just the model of 100 days, and I'm going to run it out to 300 days. Let's say 360 days, just to make it close to a year. So now I've got the same parameters here. I'm reducing my lambdas, and I'm staying in lockdown, and I'm going to run that program with that and see what happens if if I don't take my lockdown off at all. When I run that, it takes a while. Notice here that in fact, if I don't take off my lockdown, I'm going to limit, I'm going to have my peak at day 60 like I did before. My first inflection point is day 34 like before. But now notice that this starts fluctuating a bit and it goes down much more slowly. One characteristic of SIR diseases is that if R0, our reproduction number, is bigger than 1, then the disease remains endemic. It doesn't go away. It doesn't go back down to 0 like predicted in the models where R0 is less than 1. And notice by having asymptomatic cases here and allowing those asymptomatic cases to stay in the population and propagate the disease, these asymptomatic cases are going to be responsible for keeping this disease in the community. So what we have to do is not only be very careful about getting out of lockdown, don't just go back to your old ways. Once you are out of lockdown, you still have to try to find those asymptomatic cases because they can keep the disease going forever. On that depressing note, well, it's a happy note. We have to keep fighting. So thank you for watching, and I'll see you in the next video. Bye.